My talk is about random walks on integer compositions and interval partition evolutions. This talk is mainly based on a joint work with Matthias van Kuyl from Oxford, and our preprint is available on arXiv. We also mention results from the other two preprints here. To start with, let me remind you the scaling limits of a simple random walk on integers. A simple random walk could jump to the left or to the right with equal probability, and Dunsk's theorem tells you if you rescale the path of the simple random walk, both the time and the space, then this rescaled process will converge in distribution to a limit, and the limiting process is a Bernoulli motion. So today, my result is also a scaling limit result of certain random walks in a similar spirit, but our random walk is on a certain combinatorial structure, namely integer compositions. Recall that a composition of integer n is just a sequence of positive integers which sum up to n. So a composition could also be represented by a diagram of piles of boxes. And the difference from composition and partition is that for a composition, we care about the order of these positive integers. So this diagram could be viewed as it's also an ordered version of the Young diagram. If you discard the order, then you're back to the notion of the partition. We can view the collection of all integer compositions as a graph. On this graph, there are infinitely many vertices which are given by the collection of all integer compositions. And we put an ordered edge from composition sigma to lambda if lambda could be obtained from sigma by adding up one box, thinking about this diagram. The graph of compositions is just an example of so-called branching graphs. Other branching graphs also include the graph of partitions, Pascal triangle, or the Schur graph, etc. There are already a good collection of literature about limiting scaling limits of random walks in particular on the graph of partitions. And it turns out this theory is also very important in the study of algebraic combinatorics and representation theory. So a natural question for us is to understand the scaling limits of random walks on the graph of compositions. Let me now give you a precise description of the random walks we want to study. We will use the language of the famous Chinese restaurant process model of Pitman and Dupin. In that language, let's consider a Chinese restaurant where tables are ordered in a line. New customers will arrive in this Chinese restaurant one by one in continuous time, and the rule of their arrival is determined by two parameters, alpha between 0 and 1 and theta positive. For any existing table with n customers, a new customer will arrive and join this table at rate m minus alpha, and a new customer could also arrive and start a new table. At rate theta, he will start a new table at the very left, and for other these specific positions, a new customer could also arrive and start a new table here. So we notice that the difference from our model and the classical Chinese restaurant process is that we care about the order of these tables. If you discard the order of the tables, then we're back to the classical Chinese restaurant process. Another difference is that in our model, each customer could also leave the restaurant at rate 1. So the total number of customers is fluctuating. At each time t, if you record the number of customers from left to right, then you get a sequence of ordered positive integers. In other words, you get integer composition. So we can view this process as a random walk on compositions. We call it a PCRP. Our main result is about the scaling limit of the PCRP. We find that if you rescale it, then it will converge in distribution to a certain limiting process. To understand this convergence and the limiting process, let me now give you a further interpretation of this Chinese restaurant model. So, in fact, for each composition, a sequence of positive integers, it is associated with an interval partition, which is a collection of consecutive open intervals whose lengths are just given by these positive integers. So in this point of view, we can also understand this Chinese restaurant process as a process in the space of interval partitions. And in fact, our theorem here is just about the convergence of passes on the space of interval partitions, and the limiting process will be an interval partition valued process. We call it SSIPE. Here I put a collection of more information about the space of interval partitions. It is a metric space. And let me now give you a purely continuum construction of the limiting process, the interval partition valued process. We first put a level process X with positive jumps. At each jump of X, we're associated with the excursion so that the size of the jump is equal to the length of the excursion. We imagine this excursion is evolving vertically corresponding to the spindle shape so that the width of the spindle shape is given by the value of the excursion. If we imagine the time direction is going up vertically, then we can also interpret this picture as a Chinese restaurant model, so that each excursion corresponds to a table in a Chinese restaurant, more precisely a time or level X or minus. A new table is put in this restaurant, and the number of customers of that table will evolve according to the excursion. At each time t, if we record the size of all the tables that are alive at that time, then we naturally get interval partition. So this picture will correspond to interval partition valued process. Like here, I will show you a simulation. On bottom right, you see this level process marked by excursions, and this corresponds to the interval partition evolution showing on the top left. Back to our slides, we have obtained a number of properties about the limiting interval partition evolution. In particular, we have interesting properties related to the stationary distribution. If you renormalize the limiting in SSIPE and put a Lamperti type time change, this time change is very similar to those between a self-similar process and Levy processes, then we find that the renormalized time change process has a stationary distribution, and we call it the PDIP. This PDIP is law of a random united interval partition. We have more properties about the stationary distribution here. In particular, it is related to the famous Poisson-Dirichlet distribution. Finally, let me present the application of our results in the study of population genetics. In the 1980s, there is a famous population genetics model called the labeled infinitely many neutron islands model with the parameter theta. The basic setting is as follows. Mutations occur with intensity theta divided by 2. The type of each mutant offspring is chosen independently according to a probability law on the space of all allelic types. Each n-curve represents the evolution of the relative frequency of all types in a population by a Fleming-Veil process. That is a process mu taking value on the space of atomic measures on the space of allelic types, so that at each time mu t is the atomic measure which gives you the statistics of relative frequency of types at time t in that population. They show that this process has a unique stationary distribution given by the Piedman-York distribution with the parameter 0 and theta. In fact, Piedman-York distribution could be extended to a two-parameter family with parameter alpha and theta. So a natural question is, can we generalize this population genetic model to a two-parameter family as well? To see how we solve this problem, let me remind you this picture that we construct this into partition evolution. Now we just modify this picture a little bit. For each jump, for each excursion, we also show it associated with a random allelic type chosen independently according to a certain probability law nu zero on the space of all types. And here in the picture, the type is represented by its color. Then this picture could also be understood as showing the evolution of allelic types in a population, so that the frequency of all different types at time t is just given by the statistics of the excursions alive at that time t, like this atomic measure here. In this way, we get a population genetic model, and it turns out we can prove that the depersonalized process of this process also has a station distribution given by the Pitman-Yaw distribution with parameter alpha and theta, and we can show that when alpha equals to 0, our model corresponds to exactly X-ray and Kurz model in the 1980s. To summarize, we have constructed a two-parameter family of interval partition evolutions, and they are the scaling limits of random walks on the graph of compositions, the scaling limit of such Chinese restaurant processes, and we have an interesting application which generalize the labeled infinitely many neutron Alice model of each Kurz. Thank you for your attention.